Oh, hi Peter.
Hi.
How's it going?
Good, good. I assume you're following the OpenAI's announcements dribbling in.
Mm, yeah. Not that much though. I just like reading some like the tweets and stuff like that, but I haven't played with stuff they have released.
A fun way to release stuff.
Yeah, indeed. Hi Mash.
Hi, Hi, Santiago. Hello,
How are
everybody.
you?
Doing well. Just woke up a little while ago. Been partying really hard recently, so um, please don't expect me to engage hard today.
It's okay. Let me share this in a moment. Announcements. Um, okay, we're just three people right now. Maybe we can. Okay, here's Nasari, Michael. Okay, there's people coming in. Cool.
Hey guys.
Hello. Very happy because we have been meeting now for more than 1 month, which is great. I guess it's like an accomplishment to be able to do this for a whole full month. Um, Maybe we can wait a little bit. If not, I can start also, but for Eddie, because here it is. Here's Eddie. So yeah, as I was saying, today is the fifth session, and the agenda of today is to finish the last details of attention mechanisms and then start with implementing a GPT model from scratch, basically putting all together the things that we have been doing so far. I don't know, Eddie, if you want
Yeah,
to
yeah, I'm
take
fine.
it from here.
Hello, good morning, good afternoon, everybody. Let me share my screen.
Yep.
Please let me know if you can see it.
Yes.
I prepare this time a different approach. I want to make a kind of more hands-on based approach, and it's the first time when I'm using this tool. And I apologize from the beginning if some parts of the screen will not be very clear or nicely formatted, or but I think it's a good way. Okay, so we talked last time about multi-head attention, and I think it's a good idea that I need to go one step back from last time. So the idea of the multi-head is to divide the attention mechanism we've seen last time in multiple heads which work independently. So we have an input and we have this matrix 6 times 3, 6 rows, 3 columns. We have 6 tokens. Your journey starts with 1 step. We said that we initialize these matrices, trainable matrices, W, query, key, and value. These are the matrices from the model. If I go back here, so I run the code and I executed this multiplication using the code. And let me so this is the give me a second to find where is the keys. Here, yeah, okay. So if I am printing here all these matrices. I took all these matrices and I put it in so these are the matrices which I put in Santesh. I multiplied and I got these query values and query matrices. Then each matrix has a dimension 6 rows, 2 columns. We decided to have a output dimension 2. Then we compute the attention scores. Attention scores, which, if you remember, basically we want to encode the importance of a word or of a token in regards to all the other tokens within a sentence, which means that by definition, this attention score should be a number of token or number of token matrix, because every word should be related to all the other words. For example, this number here, 178, which corresponds to the third token on, basically encodes, if we take the word journey, which is the second word here, which means the second row, and we take the third, we want to see what is the attention this word should pay to the third word, which is begin. We have this number 178. Computation of this attention score is done with this dot product multiplication. We take the query matrix and we multiply with key matrix, which we need to transpose because these are the laws in matrix multiplications. Then the next step is to scale. We discussed last time, it was a good discussion about why we need to scale in order to avoid the explosion of the values. And we apply optionally dropout and softmax. Basically, just to recap, softmax requires that all the values within this matrix above the diagonal will be replaced with minus infinite, which when we apply softmax, then their values will become 0. And this is what we want to, this is how we implement the causal attention mechanism we also discussed pretty much last time. And see if I have something else, yeah. One second, please. Sorry for that. As I said, it's the first time when I'm using this whiteboard application, and I'm not very. Yeah, so we are on the attention scores. Let me make it a little bigger. Okay, so we said that we compute these attention scores using this matrix multiplication. Then we need to compute the attention weights. We need to by applying softmax after we changed the elements above the diagonal with minus infinite. And the last or the target of this exercise is to compute the context vector for every element. I maybe should also run in parallel with the code to make it. So these are the scores which are computed, and then we apply softmax, and then the author says, okay, let's implement all this code into a class. And Sebastian put all this code into a class, encapsulated all this code in a class which is called self-attention V1. And this is the code of his of self-attention V1, which I'm running here. And we get this context vector. And then, in order to, the author said, okay, let's use a better module from PyTorch and to improve its self-attention V1, and he implemented self-attention V2 class, which he changed the models from neural networks in PyTorch with linear layers, which seems to have a better optimization for the weights and a more stable initialization scheme also for the training. And here we discussed last time about 2 times normalization, and so while we're running the code, we have first normalization where we reach to the second normalization minute. So now we compute the context vector using the second class. Of course, we have different values because we have different weights. We use different initialization schemes. So we computed the context vector using the SAV2, and then we say, okay, let's apply the causal element to this this attention mechanism. And from now on, we'll use the values of the matrices generated by the SAV2. This is important. And here the author presents 2 options to implement this causal, let's say, dimension of the attention mechanism. One is using a mask using trill function. And then we multiply the mask with attention weights. And once we do this multiplication, some of the values will be 0. And basically, we lose the previous normalization we did in the class itself. And then say, okay, in order to give a meaning to these values, after we apply the mask, we need to normalize it again. We need to normalize with attention weights again, and by dividing each element to the sum of in each row. So this was the first approach to apply the causal aspect, or to implement the causal attention using this approach, which, as we can see, has multiple mathematical operations and requires 2 times to normalize. And a better approach is to use a property of the softmax function in order to implement this masking, and this can be done. First, we take the attention scores which are unnormalized, so original values, and then we mask them. Still, the values are not normalized, and then we apply the softmax. And if we apply the softmax to the masked results, we get a matrix from one step, basically, by applying this function. And also the values are normalized, which means the sum of the elements each row is 1, which means that we can read this matrix as a probability distribution matrix. So we can say that for the third token, when we want to read this attention weight matrix, and if we take the third token, this third token, for the third token, the first token, which is has an importance of 25%. The next one, journey, has an importance of 37%. The third one, 36%. So we can read these values as probabilities for every given token. And then once we have this attention weight matrix, we can compute the context vector, which is basically the target of the entire exercise. For every token, we want to compute an extended or enriched vector to provide us insights not only about the meaning of that token, but also the relationship of the token in regards to all the other tokens in the input. And this context vector calculation is done simply by multiplying the attention weight with which we just computed with the value matrix, which was computed at the beginning, if you recall. Okay. Now all this code also can be embedded into a class, can be encapsulated into a class. And also we want now to support batches. Batches means to be able to, the weights to be able to process multiple sentences in the same time. In this case, the first dimension of this tensor, which is 2, let me mark it. So this 2 represents the number of inputs, 2 sentences. Second means the number of tokens. Third value means the what is the embedding dimensionality. And all this code now is encapsulated into a causal attention class. And the result of running this self-attention class is then we get, if we go to the code, self-attention v2, apply softmax, 2 versions. What is the class? This is the class, causal attention class. And if we print the context vectors, we have now this, but maybe I run it on a. I think I'm too far with the code here. But this is what is the error here. So if I'm running class attention, so we initialize the matrices here. We define the shape of the tensor. We calculate the matrices, keys, queries, and values. We compute the scores by multiplying the queries with key transpose. We apply the mask. We compute the weights by applying softmax function. We apply also dropout. I skip dropout for simplicity, and we compute the vector. I don't know. Maybe I did a copy paste, a wrong copy paste of the final context vectors in this presentation. I apologize. Sorry for that.
Okay.
Yeah. Okay. Okay. And now we want to extend. This class or this. Basically, what we did so far is so-called single. We can call it single head attention. It's called single head attention. We can call it single head attention because we computed a single set of matrices, query, key, and value, and based on this single set of matrices, we compute attention scores, attention weights, and then the context vectors. One set of context vectors. Now, so basically, we have, if we can say. So we have only one head, which is pay attention to one token at the moment, but we can extend this logic and say, okay, we have a token, but what if we have two heads, which are paying attention to the same token? So then this is how this multi-head attention idea came into place to implement multiple entities or multiple entities which should pay attention to various aspects of content. So the solution or the implementation is by running or creating multiple instances of the previous self-attention mechanism, which we just discussed, by stacking multiple heads one on top of the other, and then to combine the output of each instance. So if an instance generates each instance will generate context vector. So we concatenate all these context vectors to get, let's say, a much richer result. So with as this the diagram shows, basically we have an input, and instead of computing only one set of weight matrices for query, keys, and values, we compute multiple sets. In this example, 2, and we will get 2 sets of weight matrices, and then we compute. We'll have 2 sets of queries, keys, and values. And we've seen that queries and keys are used for dot product to compute the attention score, and value matrix is used to compute the context vector for a given token. So basically, at the end of the day, here we apply masking and dropping, and at the end of the day, we'll have 2 context vectors. And we concatenate these context vectors to have one big combined context vector for a given token. The implementation is, I think, this is the code which I run. That's why. Okay, so as we can see in this implementation of the code, we have a 4 approach, which means that we have a sequential processing of the context vectors, which is not optimal. So an improvement to a sequential processing is a parallel processing. And parallel processing basically means to use a different approach using so-called weight split. Okay, so the idea is to minimize the number of computations. So as we've seen in the previous implementation, we need to multiply these matrices for every head. So if we have 100 heads, we need to perform 100 multiplication for a weight matrix, 100 multiplication for weight key, and 100 multiplications for weight values, which is very intentional from the computational point of view. So the idea is to have only one multiplication for the value for the weight matrix, one multiplication for the weight key, and one multiplication for the value matrix. And then once we have this, let's say, 3 multiplications, to split the result into number of heads we had. So, for example, in case of GPT-3, they use 96 attention heads. And as you can imagine, it's very computationally intensive. Okay, so the idea is that instead of doing this sequential or independent multiplication for each head, to deploy a matrix or a weight matrix which basically accumulates which has a D out, which is equal with the number of heads times number of the D out for a head, and to get a query, a value, and key matrix which has this new D out value, which basically this D out basically encapsulates both the number of heads and the dimension of a head. And then once we get this big matrix, to split it into smaller matrices, which correspond to the number of heads. The implementation of this stuff is I have another board for this one because it's a big topic.
Can I just ask a quick question about that? I think what you just said is that it's numerically identical as the straightforward multi-head attention. It's just a more efficient way to compute the same answer. Is that correct?
Yeah, it's a good question. It's a very good question. Well, we can test it out. Yeah, we can test it out to see what is the outcome from this to implementation. Yeah, it's an excellent question. Yeah, I will do it. Let me go through the mathematical implementation of this weight split approach, and then I will because I'm also curious to see if they provide different results or not. I would say, based on my intuition, that they should provide the same outcome, but I need to see it. I need to test it. Okay, so here this weight split basically is a sequence of mathematical transformations in order to incorporate within the previous tensor, to also incorporate this information that we have now a certain number of heads. Yeah, so we need somehow to incorporate this information in the way we define this tensor. So the previous tensor has 3 dimensions: B, batch, number of batches. So we had 2 examples. Number of tokens, 6 we had, and the input. So so now we need to decide on 2 variables, the out and the number of heads. The target is to get a context vector for each token in the same format like we achieved earlier, which was 3 times the out. So ahead, so this dimension, the out 6, will be basically a multiplication of the number of heads, 2 in our case, and the dimension of a head. Then again, we need to initialize. So as I said, this is the target. We need to, at the end of the day, we need to get something which has a format 3 or the out. We need to initialize also trainable matrices, which will be 6 times 6, which is the piece of the code which takes care of this initialization of these matrices in the init constructor. Then using exactly the same approach like in sequential, in the previous implementation, we multiplied the input with these 3 trainable matrices. We get key value and query matrix. And now we need to look a little bit on the dimensions of these matrices. So, so the input we have so how to read this tensor. So we have one input which has 3 rows and 6 columns. Yeah, we have the sequences I love summer. This is the text with 3 tokens. So we have this dimension of this matrix will be 136. 1 represents dimension of the batch, 3 number of tokens, and 6 the dimensions of out dimension, which basically is 2 heads multiplied with 3, which is the dimension for 1 single head. So this is the code which computes using these methods. View computes the keys, values, and queries. And now comes a critical step here is that the so-called unroll the last dimension of these 3 matrices to also to include this information, which is number of heads and the dimension of a head. So in the previous, let's say, implementation where the tensor had 3 dimensions for batch, number of tokens, and the out, the question is, okay, how do we encapsulate this information about number of heads, which is a very important information, and we don't have any way to say from the existing way of describing the tensor in 3 dimensions, batches, number of tokens, and number of dimension of our dimension, dimension of the final matrix. We don't have this information about number of tokens and number of heads and dimension of a single head. So and what means unrolling? Well, unrolling means that if we have, let's say, a 3-dimensional tensor, somehow to decompose the last dimension, which is the out, to decompose it into, which is 6 in our case, to decompose it into more meaningful, let's say, more meaningful values, which are able to convey this information about number of heads and the dimension of a head. And as we see here, the D out basically is the product, is the result of multiplication between the how many heads we have and what is the dimension of a head. So 6 in our case is 2 times 3, and we can extend the original tensor into a 4-dimension tensor, which now contains also the number of heads and dimension of a head instead of the out. So here I messed up something. Okay, so we need to reshape the original token into 4. Now, in order to reshape, to make this reshaping, we need to transpose the new tensor. We need to bring multi-head dimension in front of number of tokens. And here is something which I didn't understand 100%. Maybe somebody else is able to explain why the transpose is necessary. So here for me is a big question mark actually here. I know this is what the author says. Is not 100% clear. Why we need to change the order in this tensor? So basically we need to change the third dimension to become the second and the second to become the third. So after transposer, again, if anybody is able to answer or to explain better exactly what this alignment means of the matrices, please. I assume it's not a very easy topic. And yeah, okay. So the target the target dimensions of the new tensor will be 1, 2, 3, 3. Basically, let's say we swapped the number of tokens with number of heads. This is the code. So we apply this transpose method. With indexes, you know, Python starts with 0. The batch corresponds to index 0. Num tokens corresponds to index 1, and number of heads corresponds to index 2. So these are the method applied to all three matrices in order to perform this transpose. And now, once we have this new tensor format for this, we can compute the attention scores. Now, as you know, attention score basically is a matrix which has, let's say, 6 by 6. In the previous example, it was 6 by 6 because we need to be able to say for every token what is the relative importance for all the other tokens, which means that an attention score by design must have this shape, which is number of token or number of token, because this is what it must describe. So it must be, this should be the target, let's say, shape of this attention score matrix should be number of token or number of token. Okay, and now if we know that this should be the target shape, because this is what the attention score matrix is, as I mentioned, we need now to transpose again the key matrix. So we apply, of course, the same formula. We take the query and we matrix and multiply with transposed key, transposed, and we apply it for the second and the third dimension. So basically, so in order to, that's why, as I said here, the target is to get an attention score which has this format or this shape. And in order to do that, we need to make this transpose operation in the key matrix, and the target or the final shape for this tensor will be batches, number of heads, and then number of tokens and number of tokens, which basically will describe the scores. This is implemented in the code. This is the code here. Is implemented here with queries of the transpose dot product for each head. No, this is the right one. And then once we get the attention score, we can compute the attention weights applying the same approach. We mask the attention score to implement this causal attention implementation. We divide it by, in order to scale, we divide it by square root from dimension head, which is 3. We have 2 heads. Each head has out dimension 3, and then we apply softmax. Of course, we need to set all the values about the diagonal to minus infinity to make them 0 when we apply softmax function. So attention weight shape is identical with attention score shape because we didn't make any changes in the order of the dimensions or order of the dimensions. So the shape, the final shape will be number of batches, number of heads, number of tokens. We can implement dropout. I skip this part. And finally, we can compute the the context vector by multiplying the attention weights with values. So we get these are the shape of the both elements. We multiply B number heads, number tokens, B number heads, number token, and head dimension. This is the shape of the value matrix. And at the end, after the multiplication, the shape of the context vector will be B number heads, number of token, and head dimension. And as I said, the format of this context vector should be 3 and number of tokens and D out. So we need somehow these two elements to be merged, because if we multiply number of heads with the dimension of the head, we get the original D out. So in order to perform this multiplication or merging, we need to swap now again. We need to swap the second element with the third one and the third one with the second, which basically we perform a transpose operation. And we'll get the answer or the final format will be B number of token, number of heads, and head dimension. And last step is to combine these heads to get the original or the out by context vector. So this is the implementation. Now to answer your question. So your question was if we apply sequential and parallel approach, if the result is the same. Let's see. Let's see, where should I go back in time? So this multi-head attention, your journey. So this is the we have two heads. We have two heads here. The out is 2. Yeah. So and we have two badges. Where is badge defined? Yeah, here, two badges. Okay, what does it mean? That we concatenate the outcome of each head for each entry, and we get this tensor. That's why you have 2 times. We have 4. The out is 4 because we have 2 heads times the out for each head, which is 2. So we put the I cannot select it, but I hope it's clear. So this is one outcome. And if we go to the weight split approach, weight split approach, what is the code? So Peter, how do you read it?
Well, to me, one of the things, the way I have it in my head is like we are using this attention mechanism to get some sort of probabilities, what means that we can tweak the output dimensions so that we only had like one number per token and batch. Or we can have more, but it does not have to match the dimensions of the embedding because it's just like a probability. It's not words like we had on the input. We are going to then multiply this when we do the GPT transformer block. We are going to use these probabilities to be multiplied against embedding, so we have words back. So to me, that's one of the things that explain a little bit about these kind of switches of dimension.
Any other perspective on?
Hi. The way that I understood this one is that before we did multi-head attention, it was batch into number of tokens into number of dimension, right? And what we did in multi-head attention was we just split the number of n dimension into number of heads cross head dimension. Well, I think maybe I'll just take a few more minutes to write up something and maybe send a screenshot and then explain because I think it might be more helpful.
Yeah. Yeah, I think this comparison between if the split version and the sequential version results in the same result, it's probably true. Like probably they end up being the same. Otherwise, there should be like a big warning, like, "Hey, this is actually different." But I think it's a fun experiment to test. But I think maybe we can test it offline, or if someone is just very curious right now, test it on their own and then share. Otherwise, it might take us like we will just wait too much time
I take
right
it,
now.
Peter, as a homework. Yeah, I take it as a homework, Peter. It's very interesting. I'm not sure how the code is changed or modified in the parallelized approach. I didn't look at this aspect, unfortunately, but it's a good question, and it worth to deep dive into to find the answer. But do you have any, Peter? Do you have any? I don't know, any additional? Do you have any additional insight about your question, or it was?
So I'm pretty sure it's just a computational efficiency thing, and so that the numerical results should be identical, and of course, computational efficiency is really important, and of course, all the code has to end up being efficient, but sometimes it gets in the way of understanding what the algorithm actually is.
Yeah, I also think
so. Okay, so what I can say, just one. So the shape of the tensor in the sequential approach is 264. The out is 4. We have two heads. This is attention head 1. This is attention head 2. So two heads. Each head has the out 2. These are the first text, second text, because we have a batch of 2 again, which are identical. So the tensor here has the last dimension of this tensor is 4 lines. And if we go here in split weights, the out is 2 for a head. We have 2 heads, but the result is 262. Yeah.
The other example, did it have D out as 2 as well?
Yeah. The out was 2. The out was 2. So basically here in the sequential approach, where is the out? No. Yeah, the out is 2. Yeah, it's a good question. I think it can be a good homework for everybody, I think. But I will go deeper because it's a very interesting question. Thanks, Peter. Yeah,
Hi,
so
I just sent a diagram in the chat. Could you please present that?
Diagram in the chat. Let's see.
Okay, cool. So the way that I understood this one is that previously we had batch number of tokens and n dimension. So the final attention matrix was 6 cross 6 because we have a attention score for every single token. I think we can ignore the batch dimension for now. So in multi-head attention, all we did was we broke down the n dimension into heads. So for example, 4 cross 32. Now, what we want to do is in multi-head attention, we want to compute the attention scores for each of the heads independently. So we still want 6 cross 6 as the final attention matrix. We just want four of them. So what will happen here is that if we swap the n token and n heads, we end up with 2 cross 4 cross 6 cross 32. Now, when the attention scores are computed, we'll still end up with 2 cross 4 cross 6, which is what we want. We want for every single head the attention matrix, which is what ends up happening. And I think that's why they swap these two so that we can.
Yeah, thanks. Okay, Santiago, floor is yours. Oh.
Sure. Okay, thank you. Thank you, Eddie. That was a pretty hard chapter. I need to
It was, I mean,
yeah. Thanks a lot. So my chapter, I think, is actually nicer to understand, like much simpler, maybe not nicer because attention is also nice. So this is chapter 4, which means that we are in the middle of the book because the book has 7 chapters. And this is also the last chapter before we start training things. In the next chapter, we're gonna start like putting data into these architectures that we're doing. So this is like the last fundamental chapter, in my opinion, because then it's about like training. So it's pretty cool. I wanted to start by saying, okay, as Sebastian does with his book, like he starts teaching this stuff, like building blocks, like building a block on top of the other one. We are right now here, and the last part of building an LLM. And today's goal is gonna build the GPT architecture. So at a high level structure, we have this thing. We already spoke about tokenized text on chapter 2, as well as embeddings. Today, we're going to focus a bit more on what is happening here inside about this transformer block. We already learned about multi-head attention, but we don't know like how multi-head attention like actually fits into this transformer block. We just know these 3 pieces, but we haven't linked them yet or fully yet. So that's our goal today, and understand what is actually inside this transformer block. So same as Sebastian has been doing it, he's built on top he built on top of the stuff that were already built. So mm, so we will first start by coding the GPT backbone. This is gonna be like placeholder. Most of it is gonna be placeholder code that we're gonna then fill with the right parts. Then we're gonna start adding kind of the ingredients that are inside the transformer block. We will speak and learn what is the layer normalization and why is it useful. Then we're gonna introduce yellow, kind of the uh, far cousin of ReLU. Then we're gonna speak about how this yellow plays into account in that feed-forward network. And then we're gonna speak about this thing that is called shortcut connections, which seems pretty weird. At least they did when I first learned about them a while ago. But actually, they're quite simple once you see it on code. Then we're gonna put everything together, have a transformer block, and use that transformer block many times to have the final GPT architecture. All right. Also, since I'm presenting, I'm not super aware of what's might happen in the chat. So if anybody just want to interrupt, they can. Or if you just want to comment on the chat and someone can interrupt me and ask out loud the question that is in the chat. So let's start with the backbone. I don't know if this is large enough, but this is actually not the backbone. This is the full thing, but I wanted to put it as, okay, our end goal. We're gonna create like dummy implementations of some of this stuff here, but I wanted to have like the general path here, so the code makes a bit more sense. So let's take a look at the code in here. Well, first, let's initialize this dictionary that we're going to be using several times during this chapter. Here, we're going to define our vocabulary size, the context length, the embedding dimension, how many heads and how many layers we will have, what is the dropout rate that we will have, and if we're going to use bias term here on the query key value matrices. So I think I just restarted this notebook, so I need to remember to find stuff. So here is so we start the chapter by implementing this backbone. Is what we call the dummy GPT model. The first thing that we do in PyTorch is that we create a class. In this case, we create a class called dummy GPT model that inherits from the model, which is like the base class for all neural networks models. And this is how you do it in PyTorch. Then you want to initialize it. In case you are not super familiar with object-oriented programming in Python, this is the way that you initialize also the parent class. In this case, the torch model, NN model, and basically allow PyTorch to initialize like relevant functionality. So we want to initialize some stuff. The embedding dimension or the token embedding, sorry. We use the layer embedding, which if we see it here, the first parameter is the number of embeddings, and the second parameter, the second argument, is embedding dim. So as first argument, we put the vocabulary size because that number of embeddings, and the embedding dimension, we're gonna pass the embedding dimensions. This CFG, it's like config. It's gonna come from from this dictionary that we already initialized above, right? We do something similar for position embeddings, and dropout. We pass the dropout rate that I think was 0.1. Yeah. Then here's like the tricky part, because this is the part that is hidden in a sense. This still is like the dummy blocks, and they don't do anything yet because we need to actually create them. But since this is just the backbone, what this is doing is that we're gonna create a sequence. We're gonna stack on top of each other, in this case 12 dummy transformer blocks on top of each other. So this syntax might look a little bit weird, but I put here like what it actually does. So for example, if we just have two layers, what this operator here does is just put one on top of each other. So it would be the same as writing dummy transformer block 12 times in this case, since we have n layers equals to 12. So what we're doing is initializing these transformer blocks in our dummy GPT model. Then we also want to initialize a final norm. Why? Because we're initializing all of these things because they are part of this backbone, right? So we just did the transformer block, and we want to initialize the final layer norm that will use a dummy layer norm. We don't know yet what this thing does. We need to build it, but here we initialize it with the input size that we want. And lastly, the last thing that we want to do is the out head. That is also part of this final part of the block. And it's basically a linear layer, which takes as input something that is size of the embedding dimension, and output the size of the vocabulary size. So it's gonna be pretty big, the output size. Why? Because basically this is like this output will contain all the logics or all the probabilities for each token. And since we're doing like next word prediction, we need to sample or choose from all of the vocabulary size to choose which word we're gonna use, right? So that's why the last layer, the last linear output layer, it's pretty big. Does it make sense? Yeah. Okay. Then here we have the ingredients, but we haven't tell this dummy GPT model how to use these ingredients or in which order. That's what we do in the forward pass. So in the forward pass, we first like, okay, take the patch size that we want, the sequence length, and now we can, let me see, we can start following this order. So, okay, let's start with the token embeddings. So we create the token embeddings. Then the position embeddings. Here are the position embeddings. I don't know if this is too small for actually like being visible. But here we have the token embedding layer, then the positional embedding layer. Here it is. Then as we learn in second chapter, we basically sum at token embeddings plus positional embeddings, and that's then how we roll. Then we need to add this dropout layer. That's basically what we're doing here. Then the transformer block that we have encoded, but we can do it since we have like the dummy version here. So we add the transformer block. We're doing this here 12 times because that's the number of layers that we have. Then the final norm final layer norm. We also don't know what this thing does, but we are building the skeleton. Then the logics are what I was saying, the output layer. And then we just return the logics. Later on, we will see what we do with the logics, but that's it. That's the forward pass. And here at the end is just the helper classes of dummy transforming block and dummy layers that right now they don't do anything. They just pass the inputs, receive an input and return it as output. Nothing crazy going on in here. So this is the backbone. This is the stuff that we will try to complete. And by trying to complete, it's basically completing this dummy transforming block, make it less dummy, and the same thing with layer number, right? So that was the first goal. First goal was to do this thing. Now let's take a look at layer normalization. Let me just run this thing so it doesn't fail. Okay, layer normalization. I guess it was, well, pretty sure it was by experimentation and maybe some numerical math there involved. But people realized that they get better stability and more efficiency during training if the output of the activations of a neural network are the mean of the outputs are around 0 and the variance around 1. So that's what the layer normalization does. We have some inputs, we pass them through a layer, and some activations are involved in there. And these outputs of that layer have, like, I don't know, arbitrary mean and arbitrary variance. But if we normalize them, basically they help us having more stable training. So what does normalizing mean is having mean equal to 0 and having variance equals to 1. That is also something that is done in classical machine learning. Like some classical machine learning algorithms are more stable if we have normalized inputs. So I guess that's where the idea came from. As an example of how this thing works, Sebastian creates a small linear layer with a ReLU activation function, and we print. Where is it? Here. No. Okay. Okay. Here is the output tensor. So we have 2 batches. How is it? 6 tokens per batch. If we print the mean of each batch, we have arbitrary means, arbitrary variance. But then if we normalize them, and how do we normalize? It's basically this output, the output vector, the original vector. We subtract its mean and then divide by the square root of the variance, and we will end up with something that has 0 mean and variance 1. So if we do this, we have out. Remember that out is this layer. So if we have out, subtract its mean divided by the square root of the variance, and we print that. Oh, didn't get. Again, maybe I mess it up. Okay, yeah, I messed it up. Yeah, then we end up with a tensor that each batch has 0 mean and variance equals to 1. Then something also curious here is, so this idea of normalization is something that we use in the layer norm. Remember the layer norm we have above in the skeleton, like a dummy layer norm that we use several times. We use it once here, and then once here. So this is like a very important block because we use it at many points. But something interesting is that we not only normalize, but we're also gonna add two extra parameters. One that is called scale and one that is called shift. These parameters, we will have to learn them. How? By backpropagation. I guess it will be a bit more clear in the next chapter. That is where we're gonna train stuff. But right now, the forward pass of this layer norm looks like this. We calculate the mean of our mean inputs. We calculate their variance. We normalize it by taking the original input minus its mean divided by the square root of the variance. Here, to keep things stable and math happy, we add a small epsilon, just so things don't explode if variance is equal to 0. Basically, we have like a full tensor with the same value. That's when variance is equal to 0, right? There's no, if this is a full tensor with just ones, there's no variability, so that would be 0. So this square root, this division, would have result in infinite. So we add this small epsilon, and what we return is not the norm x, but kind of a linear regression, or kind of a linear version of it, where we have the scale parameter times the norm that we just calculated plus a shift. In the very beginning, this doesn't do anything because if you see, a scale is initialized as just a vector of ones. So we're multiplying the norm by 1, just exactly the norm, plus shift. And shift is just a tensor of zeros. So it's 1 times the norm plus 0. So at the very beginning, it doesn't do anything. But the idea is that during training, these tensors, these weights, will start moving a little bit thanks to backpropagation and gradient descent. And we will end up with kind of a linear version of this norm x that is more suitable, and it will like benefit the network predictions.
So I had a quick query here. What's the kind of a relationship between the var and the epsilon? So epsilon, they have added 1 e neg 5. Yeah. So I was thinking, why is that, and what's the kind of a relationship between var and this guy here?
Yeah, no, it's just to keep sorry, it's just to keep things stable from in case var is equal to 0. So we just want to add a small number. This could be e to the power of 1 to the power of minus 5, or it could be to the power of minus 6 or 4.
Oh.
It just so we are sure that there will be a number different than 0 in the denominator. And we want it to be small, so we don't actually like affect the math inside. It's just a little bit. We're affecting it by just a tiny bit amount. So non-negligible. Yeah.
It might be to other people, but to me, it took a while to understand that the variance is always either 0 or greater than 0. So at the beginning, I had the question that can it be just exactly 1 to the minus 5 in negative, but it cannot happen. So that's basically the idea, is to avoid division by 0.
Yeah, that is a good point. Yeah, variance is always positive.
And then
or zero.
scale and shift are the two trainable parameters. Like it's they are the LLM kind of automatically adjusts during the training if it is determined that doing so will improve the model's performance on the training task. So like it's kind of a self, yeah,
Correct. Exactly.
yeah.
So I have a little bit of intuition about that scale and shift finally. It's scaled and shifted, and then the next thing that's done is to add the skip connection. And so that allows it to shift the relative importance of the skip connection and the layer computation output. And so presumably, my guess is that at the early layers, I'm not sure which way it is. I'm going to say at the later layers, probably the skip connection is less important, so you have a higher scale. And so I'll be interested when we get to do a training ourselves to see how the scale changes over the different layers. And my bet is the later layers it's smaller, and the earlier layers. Sorry, it's the other way around. At the later layers, the training output will the layer output will be more important, have a higher scale value compared with the skip connection. So interesting to see whether that's correct.
Yeah, that would be fun to check. Yeah. Cool. Cool. Yeah, Sebastian also speaks about some bias in the variance and how this comes into play, but this is just this normalization. Some people do it, or sorry, the variance calculation. Some people do it by using this formula. Other people add a -1 in the denominator. This is like a correction that is an unbiased variance estimator. In this case, I think it wasn't that relevant. I think Sebastian does like the biased ones because that's what GPT-2 people did. So just to have similar results. Okay, then that would be the layer normalization. So now remember always think about the backbone GPT. We had this dummy layer norm. Now it's not dummy. Now it is doing something relatively simple, but it's not dummy. So we just completed a step 2. The next step is about Jello. And Jello, basically, if you remember ReLU, remember that it's basically if something is less than 0, we just equalize it to 0. We squish it to 0, and if something is bigger than 0, we just return its value. Jello, on the other side, is kind of similar, but now allows for small negative values. So now negative values can have like a contribution, a little small contribution on the learning process. That's the whole thing about Jello. And apparently it gives also better results during training. So that's why they use it. In the case of the GPT-2 paper, they use an approximation of Jello, which is this thing here, which if I remember correctly, they found this approximation by like linear fitting or something like that. I don't remember exactly, but this is the same implementation that we use. So we implement the Jello class. This is actually like, I guess I'm not sure if we're implementing this just to be strictly like the same as GPT-2 paper, because I was looking that PyTorch also has the Jello activation layer, but I guess they use a different one, a different approximation. So in this case, it's implementing this activation function is just initializing it with actually nothing, just the things inside the model, the model class, and then define a forward pass. And the forward pass will be exactly as the formula for jelly. Here we can plot it. That is, it is actually the same plot. I stole it from the book. But the actual, well, this is the yellow part. Now we have yellow, and we can now put it into practice in the feed forward network. Let's remind ourselves where the feed forward belongs. It is gonna be here. So we already covered like all of this from previous chapters. We just solve layer norm. Now we understand it and have an implementation of it. This, we also have an implementation from last chapter. Dropout, simple, one line. Skip connections, we haven't touched them. Layer, we touched them, and then feed forward. So this feed forward, what is the thing that is gonna happen in the feed forward? We're gonna use yellow there in a very funny way. Let me go back. What the feed forward does is basically we start from our original input size, then we're gonna go very wide, and then come back to the input size that we have. And the idea of this is to basically build a richer representation space. And yeah, I don't know if someone has like a better intuition of why this thing works, but in code, it's a simple collection of layers. So we start with one linear layer that, as I said, is the input size of the embedding dimension, output size of 4 times the embedding dimension. Then we pass that through yellow. Then it's gonna go from input size of 4 times the embedding dimension, right? Because that's the size that we have. And then its output is gonna be the size of the embedding dimension. So basically, we started and finished with the same size, but the contents of that is different, and it is yeah, I don't know. I'm lacking like the intuition behind this. I don't know if someone has it.
I don't know if what I'm going to say makes sense, but it looks like what we are storing for each of those numbers is like different cases in which a certain token will activate one of these yellow activations, because we have more than one for every input. So it's like creating cases in which some of them might be activated or not, and those cases are going to be learned by parameters. So I guess it's to store facts or something like that.
Yeah, maybe. Yeah. Yeah, it's like, I don't know if I have a better yeah, maybe like my analogy would be, okay, we start with something small, we then deconstruct it and try to see what is the relevant parts of that thing, and then construct the thing again from the relevant parts. That's what I understand. So of course, these two things are gonna be different, but maybe the intuition is that the outputs here will signal higher the stuff that matters the most. from these inputs. Kind of a, yeah, reconstruction process. If Sebastian joins one of our calls at some point, these kind of things are maybe good questions to ask.
By the way, now that you mention it, he said on Twitter that he had some kind of illness or some issue that didn't allow him to use the computer, so he's off. Just in case someone wants to send him a message on Twitter, wishing him to get better.
Yeah, kind of like I did, and he like replied. So like, I have been following him from like a past 3-4 years now. So yeah, we have a kind of a convo going on. But yeah, on this issue, yeah, I think so. The feed forward layer, you like intuitively you got it correct, and the folks that said with respect to storing the knowledge of the network. So like the projection is larger, so you can see the kind of like the inputs are projected into a larger space, and then it is compressed into a lower space then. So like yeah, you can see here that it just to match the original dimension, it is being compressed. So like this information or the fact is being stored, and Michael also on the chat has shared his thoughts.
Yeah, makes sense. Thanks for the explanations. Well, so yeah, that's the feed-forward network. So now we're just missing the shortcut connections, at least from the building blocks of the transformer block. So shortcut connections sounds quite complex because for me, initially they look complex. Like, okay, we had this flow and now we kind of need to maintain these two flows. Why do we need them? We need them to tackle something that is called vanishing gradients. And vanishing gradients is that usually when we have deep neural networks, remember, or I don't know, we will see in the next chapter that gradients are a fundamental part of backpropagation, and backpropagation is how we modify these weights. So thanks to the gradients is that we can modify the weights that we need to optimize. And in very deep neural networks, these gradients tend to vanish, tend to become very close to zero or exactly zero. So basically the initial layers, maybe I'm gonna make this thing here. The initial layer, since backpropagation goes from the end of the network to the beginning, the gradient is gonna be vanishing, and maybe the first layers are not gonna have very big gradients. So optimizing these first layers is gonna be very hard. And what shortcut connections do is that they fix this issue, because now they create like this alternative and shorter path for the gradient to flow through. So we don't have gradients that are very close to zero or very small. And basically this shortcut, what is actually doing is from the output of the previous layer, we just take it and sum it to the output of a later layer. So if we start from here and this yellow output something, we store this something somewhere, then continue here on linear, on yellow, and when we reach here, we are gonna take the thing that we just stored plus the current value of our tensors, and that's the shortcut connection. We just sum it later. So the shortcut is actually equal to output of one layer plus the output of a later layer. Maybe in code it will be a bit even more clear. But that's the general idea. So as an example, Sebastian does an example of a deep neural network with 1, 2, 3, 5 layers. One parameter here that is use shortcut or not, just to compare. And the forward pass, it will depend on if we use shortcut or not. But the forward pass, basically, we store here a value that we're gonna use for shortcuts. I know, yeah, we store here a value of the layer at the current state. And then if we have shortcuts, the current state, we sum it to the value that this state was before. I don't know if I explained it correctly. And if not, it's just the value from the state. Let's see how it looks when printed. So this is without the shortcut. The gradients are small. They start small and they get even smaller on the first layer. So something like the thing that we saw here. And if we use the shortcut, gradients start even bigger and they still get smaller, but not that much. So this is still like a relatively big gradient. That's what the shortcut is doing, is helping us maintain these gradients to be different than 0. Any questions around here?
Yeah, these are like the residual connections in the ResNets.
Yeah, it's the same. It's the same idea.
Yeah.
Yeah, shortcuts are also called residual connection or skip connections.
Yep.
Okay, and so then we just, let me put this picture again. We just completed the implementation of these 5 things. It wasn't that hard. And these five things together, if we put them in the correct order, we can create the transformer block. So that's the idea here. Then, where is it? To add everything together and basically create a transformer block. So remember, in our GPT backbone, we had this dummy transformer block. Now we're gonna make it less dummy by adding the things that are inside of it. So what are those things? So what are those things? It is a layer norm, multi-head attention, dropout, skip connections, layer norm, feed forward, dropout, skip connections, and later on we will have these final outputs. So in code, we create a class called transformer block that we're gonna use it later on in the whole backbone. We initialize all the relevant stuff about attention from multi-head attention from the previous chapter. So no need to go into detail. What is inside here is the stuff that we just covered. Then we also initialize the feed forward, the norm 1, the norm 2, the dropout, etc. And in the forward pass is where we see how we put in order all of this stuff. So we start by storing this shortcut so we can have it, use it when it's needed. And then we initialize the layer norm. We start by the layer norm here. Then the second step is the attention, that is here. Then the dropout. Then in the shortcut, we just take current value plus the shortcut at the original input back. So this is the skip connection, basically. Then we, again, here, this value stored as shortcut, continue with norm2. Here's the feed forward, so here things get very big, then very narrow again. Then again, a dropout. And here we have another shortcut. So we repeat this operation. We add the original input back. And finally, we return X. And this is the transformer block. This is gonna then be called 12 times, at least for this GPT small. But this is the famous transformer block in the GPT model. Let me run it. So we successfully implemented these things. Now the last thing is to, one funny also input insight is that we start with a shape and in the transformer block, we start with one shape and we output another shape. A shape that is actually the same, but the contents of it is actually a different object. It's just the same size, but it is a different object. It's just, as I put it here, is just an augmented version of the context versions that we discussed on the previous chapter. So yeah.
Does anyone have an idea about why the dropouts are in those places? Like, it looks a little bit weird to me that they are at the end of each of the sections of the transformer block. I mean, I understood the one that we wrote inside the multi-head attention because it's in order to make it not see the entire input, and there must be a reason why they are here before we add the connections back, but I didn't quite get that part.
Yeah, I think there was a comment that it was due to regularization. So to avoid overfitting, so just to forget a little bit of information that we got from multi-head attention, and then also here from the feed forward, forget a bit of information, so regularize the model. I think in the book, they also mentioned that in the first implementation of the transformer, in the original one, dropouts were before, if I'm not wrong, like before before the multi-head attention. But I'm not sure if I remember correctly.
Yeah, there was some differences in the original versus there was some recent, not recent, but a couple of years back research that also came out that played around with the positions of dropout and layer norm, and they experimented and empirically they found out this is the best layout that has to be followed. I will link the research if I found it, if I find it. But yeah, that's the reason.
All right. So yeah, this is the transformer block. This part here. Then, well, we're 10 minutes above the 90 minutes, but maybe, well, we still need to talk about generating text. but I'm not sure. I always tell people not to pass the time, and now I'm doing it. So, what do you think? Should we stop here and continue next week, or spend a bit and finish? What do you say, Peter?
Next week.
Next week?
Yeah.
Let's do it next week then.
Notice the number of people on the call dropped steadily too.
Let me check. That's true. Yeah. Yeah, let's do it next week then. It's just the last part, very interesting too. Is we're gonna generate text, and we're gonna see that the text that we generate is pure gibberish. So it's means that we need to train it, and that's basically the next chapter. So I believe this will take me at much 20 minutes. So maybe we should pick which, if there's a volunteer for next chapter for the pre-training large language models, pre-training on labeled data. Someone wants to lead it.
Don't all step up at once.
Yeah. Carlos, great. I think it would be great, yeah, to see it from your side. Nice. Then that's it. If you want, Carlos, I can reach out to you on LinkedIn, or I saw you also on Blue Sky, so I will find you, and we can discuss it if you want a couple of days before the meeting. So if I can help you with anything.
Yep, sure. Thank you.
One question, Santiago, if I may, just a quick question. I mean, some of this stuff you know already. I was curious as in what were your new insights that we had from this chapter? What were the things that you didn't know much before that were aha moments for you? Oh, I was curious about that. What were things that really struck you?
So to see it from step by step was very nice, because I've seen it from the whole picture. Like, just look at this whole picture and understand the whole picture. And now we're building on top of things, so we can also kind of experiment on the little things and understand their role better, and like input size, output size, and what is happening kind of in the inside. This is very refreshing for me, because now like the stuff clicks better, if that makes sense.
Yeah.
Because if we just start from like this thing, and it's like, okay, we need to take care of everything, so we start thinking about skip connections about this thing from the very beginning, and multi-head attention. So imagine you start like, okay, let me code the layer norm, and then okay, now let me code the multi-head attention, but taking into account all the rest. Here in this way that the book is structured, we just go in isolated pieces and then just put everything together. And for me, that's the nicest part.
Got it. The block by block approach of building it. Got it.
Yeah.
Thanks.
I did a course on edx.org that's organized by Databricks, and it's a course about LLMs. And the issue is that I mean, it's very interesting as a training course, but the sort of the first thing that we did was to take a GPT model already created and just load the GPT-2 parameters and try to do things like before training, see that gibberish thing, then train, fine tune, all of that. But at the end, I was like, I don't have I don't have an idea of what's happening inside this. It's just like a very big black box. And I think that Sebastian approach is very cool because I still need to work a lot on this and do the entire process a few times, because it still is a lot of pieces, and how is really different than classical programming, where you have a variable and you know what it is. Here we have like a ton of parameters, and I don't know what's gonna happen with them. But at least we are seeing all the pieces. It's not like a black box.
Yeah. So yeah, this is really an under the hood approach. Got it. Thanks, folks.
Carlos, will you also be running the code? Like I see for the pre-training on unlabeled data, there's some training code that's also associated with that. So will you be using Colab or Lightning AI to run it or show us?
I haven't done that. I'm working on chapter 4 for the moment. I haven't still done chapter 5. But
Okay.
yeah, if you have any suggestion, I'm happy to follow it. I guess I will try to do more or less what we have been doing in the sessions, which is try to see the parts that are relevant for the training process and execute them and try to comment on them.
Okay, cool. Thanks.
Yeah, just a suggestion, Mayank, if you already have the background, you can also team up or support Carlos. Like what I tried to do very weekly in one of the sessions. But yeah, I'm guessing you have some background, so it'll be great to have your perspective as well.
Yeah, I may try to load up on Lightning AI or Colab the code, and we can see the steps, like the variables that we discussed today, the queries that we had. So I think so we can delve deeper and like see the logs of the trainings, and yeah, we can extract insights from that too.
Maybe we can all make it a little bit more interactive, because now we're getting to the fun stuff. Let's all try to do it and prepare for it as a study group. That way we can all potentially support Carlos and share any interesting things that we see ourselves. I'd like to.
Yeah, true.
Sounds good.
Great work, Santiago and Eddie.
Thanks, folks. Thanks, Santiago. Thanks, Eddie.
Thank you.
Cheers, everybody. Have a fantastic week ahead.
Yes.
You too.
You too. Thank you all.
Thank you.
Take care. Bye.